Welcome to this new lecture on statics ME 106. And previously, we were discussing about the moment of inertia, and we claimed that why this moment of inertia is equal to r square dm. So we claim that that the moment of inertia is actually given by this integral. So why this moment of inertia is equal to r square m. Okay, so this we can intuitively explain by considering this particle of mass m, and it is basically rotating about this axis z at a distance r. And please note that this distance r is a fixed distance. As this particle moves, rotates around this axis, okay, it is always at a fixed distance r. So all the mass of this particle is actually located at a fixed distance r from this axis, and it is rotating. While it will going to have some angular velocity. So we assume a single particle only. As you can see here, that it is a single particle, and this single particle has a mass m, which is rotating about the z axis at a fixed distance r, and it has an angular velocity omega radian per second. But we also know that while this particle is rotating in a circular track uh, around this vertical axis, it will also going to have a tangential velocity which is given by r omega. So the linear kinetic energy will be given by half mv square, and you have to note that this m here represents the inertia. So m actually represents the inertia in linear dynamics. But as soon as you will going to convert this kinetic energy, linear kinetic energy expression into rotational kinetic energy expression, okay, you will going to substitute in place of v r omega, which will become r square omega square. And so we see that in place of m, while we are dealing with rotational kinetic energy, in place of m, now the product m r square has actually appeared. So this gives us idea that in rotational dynamics, inertia is not just represented by the mass m, but it is represented by this product m r square. And so this product m r square appears so frequently in rotational dynamics, uh, or systems that undergo rotational dynamics, that it has been given uh, a an entirely a unique symbol, okay, which is known as given as I subscript m, or maybe in some textbooks it is given as J. So this term MR squares appear so frequently in rotational dynamics that it has been given a uh, special symbol IM or JNB. This is known as the moment of inertia. Okay, so you have to just remember that why in a moment of inertia is given by the product R square dm, because in rotational dynamics, inertia is not just represented by m, but it is represented by the product mr square. So this means that the inertia is not just only depending upon m, but it is also depending upon the location of m, or you can say how the mass is distributed in the geometry. Okay, so this formulation, you know, r square m or r square dm was for a single particle. But we know that when we consider rigid bodies, and rigid bodies, for example, a plate is a rigid body that has finite dimensions in x and y, and this plate is basically consisting of lot of particles. It is made up of many infinite number of particles, each having some mass dm, and and these particles are located at different locations, okay, measured from some kind of an axis, for example its centroidal axis. So since there are infinite number of particles, each of mass m, in a rigid body, we say that uh, we have to use integration in order to uh, calculate the moment of inertia. We have to use integration, so we apply integration over r square dm. Okay, and while we have to make sure that this r approximately remains same for the entire uh, rigid body. So this means that the entire mass of the rigid body should be located at a fixed, almost at a fixed distance. For example, if you consider this circular disk, okay, and you are calculating the moment of inertia about this axis which is perpendicular to its plane and passing from its center, okay, then in order to use this formula, because this is a rigid body, okay, it is not just composed of one particle, but it is made up of many such particles, infinite number of particles. So if you want to use this formula, we have to use a differential element, uh, in which the mass is actually located at a almost at a constant distance from the axis z. And we see here that if we consider this ring element, then the thickness of this ring element is of differential level dr. Okay, this thickness is actually dr, and it is so small, of differential size, that we can fairly say that the entire mass of this ring element is just confined within this small thickness dr, which is located at a fixed position r from the center of the disk. So when this condition is satisfied, we can use this formula, okay, integral r square dm, because here when this formula was established, this mr square was established, uh, we saw that this r was actually fixed. Okay, so having said this, let's move on uh, to problem number uh, 10-4, F10-4 of your textbook, RC Hibbeler 12th edition. And here we are actually given this shaded area, which is shaded in blue color. And at once you can realize, if you recall some of the points from chapter number 9, you can realize that a function is defined here, that is y cube equals to x square. So a function is given here. Okay, this the equation of this curve is defined here, and this gives you idea that we have to use integration in this problem to find the value of second moment of area about the y-axis. So we have to find the second moment of area about the y-axis. So you have to locate where is the y-axis. This is the y-axis. The vertical axis is the y-axis, and about this we have to find out the value of second moment of area. In other words, we are trying to find out that how much resistance this area has against bending about the y-axis. And please remember that second moment of area is only calculated for areas. Okay, it has nothing to do with volume. So even though if this is a beam like this, which has a depth into the page, okay, then you can realize that this beam being prismatic, it has same cross sectional area at each location in the direction of its depth, that is into the page. So it will going to have the same cross section area. Therefore, uh, the second moment of area is only related with the cross section area. Even though if you are dealing with a volume that has a depth into this screen, it will not going to uh, do any difference in your calculations, because you are only concerned with the cross sectional area. which you can take at any point along the depth direction. And second moment of area is purely a geometrical parameter that depends upon only the cross sectional area. So let's first redraw this figure, and use a strip. As we have seen that we already have solved these kind of problems in chapter number 9 by using a differential strip element. So the function was given to us, and this gives us idea that we can again use a differential strip element to come up with the value of the second moment of area for this cross section. Now, unlike chapter number 9, in chapter number 10, when you are using the differential strip, you have to be very careful, because here the choice might not be arbitrary for you. Okay, so you could be restricted, you know maybe you could you could be asked to calculate the second moment of area by using only the vertical strip or using only the horizontal strip. So the choice might not be arbitrary as it was in chapter number 9. So you have to be careful that what kind of strip you are using. Now, for example, in this case, in this problem, we are asked to find the value of second moment of area about the y-axis. So you have to consider the rectangular strip in a way that it remains parallel to the y-axis. This means that you can only consider a strip that is vertical, because only a vertical strip can remain parallel to the y-axis. And why is this so? Because you see that Iy, the second moment of area about the y-axis, is actually given by this expression, integral x square dA. And the this x is actually representing the moment arms. So now this strip, which is now parallel to y-axis, and why we have considered a vertical strip, because we were asked to find the value of second moment of area about y-axis. So we have considered a strip that remains parallel to the y-axis. And why we have done this? Because in this way, the moment arms measured from y-axis along the length of this strip remains the same. Means they have the same value, same length. So you see each one of this red line has almost the same length up to the centroid of this strip. It has the same length, and these moment arms are actually measured along x-axis. So you see that if you define a point here, it will have a value of x measured from the origin. Similarly, this value of x will be same. This value of x will be same. This value of x will be same, and this value of x will be same. So the moment arms measured from the y-axis, and along the x-axis, the moment arms have all of them have the same value. So when this this point when is satisfied, then you can use this formula to calculate the second moment of area about the y-axis. So now we see that since this condition is satisfied, fulfilled, if we consider this strip to be vertical. However, if we considered, if we would have taken this kind of a strip, that is, you see, horizontal strip, not which is not parallel to the y-axis, but it is now parallel to the x-axis. So if you have considered this kind of a strip which is not parallel to y-axis, but it is now perpendicular to y-axis, and it has become parallel to the z-axis, you you would notice that the moment arms, when you measure the moment arm from the y-axis along the length of the strip, you will see that at each and every point the value of the moment arms is changing. So you see, this is actually changing. The moment arms are now changing. The moment arm here is this, then at this point the moment arm will be of this length, at this point the moment arm will be of this length, and you see that the length of the moment arms measured from the y-axis along the x-axis, they are changing, they have different lengths. So so this is not satisfying the condition of equal moment arm. Therefore, in this case, we cannot use this formula directly. So you cannot use this formula now directly. Why? Because the value of the moment arms measured along the x-axis, that is these, is of varying nature. They are changing, and therefore this formula cannot be directly used now. So instead of this, we are going to use this parallel axis theorem. So we stick with our first uh, assumption that we are using a vertical strip that is parallel to the y-axis. So now you have realized the fact that if you are if you are being asked to calculate the second moment of area about the y-axis, uh, then you have to consider the strip that is parallel to y-axis. And if you are being asked to calculate the second moment of area about the x-axis, then you have to consider the strip that is parallel to x-axis in order to satisfy the equal moment arm condition. Therefore, we consider the vertical strip here, and we say that this strip is intersecting this curve, okay, at a point which is equal to xy. So this strip is intersecting the given curve at a location xy, or at a point xy on our diagram. So this red point is x and y, has coordinate x and y. So please remember that you have to measure each and everything with from the origin. This is the same. This is the practice that we are being observing from chapter number 9. So we have to measure each and everything from the origin. So from origin, this length is 1 meter. This length is y. Okay. So the length of the strip comes out to be 1 minus y. So this is the length of the strip, 1 minus y. And the thickness of the strip is measured along the x-axis, which is dx, right? So since my condition of equal moment arms is being satisfied here, the moment arms measured from the y-axis along the x-axis remains of the same length everywhere on the strip. So the condition of equal moment arms are satisfied. Therefore, I can directly use the formula integral x square dA. Uh, you know for Iy, and the differential area of this strip will be length of the strip, that is 1 minus y into the thickness dx. So you see, this is very similar to the case that we discussed just on the previous slide. Here, let me give you again a review. Here I have told you that this we have to consider an element while we are calculating the moment of inertia. We have to consider an element that has the mass located at one fixed distance from the axis of rotation, that was r in this case. So this is the radius of the ring element that we have considered here, and while the thickness of the strip is very small, it is equal to dr. So that is why, since the thickness of this ring element is very small, dr, we say that the mass of the ring, all the mass that this ring consists, is actually located at one fixed distance r, and so therefore we can use this formula. So this same argument is actually followed here. These moment arms remain the same from the y-axis. So when these moment arms remains the same from the y-axis, we can directly use this formula, otherwise not. So therefore, since the condition is satisfied here, we are using Iy equals to integral x square dA, where dA is 1 minus y dx, which is the area of the strip. And so our integration becomes x square, and in place of dA we can write 1 minus y dx, uh, and we are integrating with respect to x, so the limit on the x-axis is 0 to 1. Okay, so from it is 0 to 1, we have to integrate with respect to x, so we have to eliminate this y, and from the given function we can write that y cube is equal to x square, so y must be equal to x raised to the power 2 upon 3, and we substitute this value of y equals to x raised to the power 2 upon 3 in this equation. So we have x square 1 minus x raised to the power 2 upon 3 dx integral, and the limit is 0 to 1. But this is not the most simplified form of the integration. Okay, so we solve it a bit more. Okay, this x square is being multiplied with this, and then this x square is being multiplied with this x raised to the power 2 upon 3. Okay, and we have two very simple integrals now. So integral 0 to 1 x square dx minus integral 0 to 1 x raised to the power 8 upon 3 dx. Okay, and this is equal to iy. So you just integrate these simple integrations with respect to x. It will become x cube upon 3. The first integral will become x cube upon 3 minus the second integral will become x to the power 11 by 3 divided by 11 by 3, and you take the limit from 0 to 1 and solve this, and you will get the result iy. So iy is 0.061 meter square. So the integration and the problem reduces to a very simple one if you have cleverly selected the strip. Okay, so we have the value of iy, which is 0.061 meter square. The, so these integration were very simple. Okay, but what if we have considered a horizontal strip? How this problem can be solved if we consider a horizontal strip instead of this vertical strip that is parallel to the y-axis and that is satisfying the condition of equal moment arms. So let us solve problem F10-4 using a horizontal strip now. So you see here that I have considered a horizontal strip. Okay. Now this time the strip is actually parallel to the x-axis. Instead of being parallel to the y-axis, it is parallel to the x-axis. But I'm still calculating IY. Okay, my purpose is to still calculate IY. And I know that I can calculate IY much more easily if I would have considered this strip parallel to y-axis as I have done it uh, on the previous slide. But just to give you idea that how can we get the value of IY if we are considering a horizontal strip that is now parallel to the x-axis but not parallel to the y-axis. So here you see that I have defined the centroid of the strip. Okay, this centroid of the strip has centroidal axes x dash and y dash. Okay, this differential element, which is in form of a rectangle, it has a centroid. Okay, that has a centroidal axis x dash and y dash, and this x dash you can see is parallel to x axis and this y dash is parallel to y axis, and the thickness of the thickness of this strip the thickness of this strip is dy. And again, this strip is intersecting this curve at a point xy. So if the length of the strip is x, its centroid x tilde will be equal to length divided by 2. So the centroid x tilde for this differential element will be x upon 2. So now you see that the moment arms, okay, they are actually not, you see they are actually not of the same value. For example, here you can see that it has a length this. At this point, the moment arm has a length given by this. At this point, right at the centroid, okay, it has a length of this unit. So the equal moment arm condition is not satisfying. Okay, so therefore I know that I cannot use this formulation. I cannot calculate Iy by using directly a integral x square dA. Okay, so I have noticed that the moment arms measured from the y-axis changes as we move along the length of the strip. So you see that the moment arms are changing, they are changing their length. So the condition of equal moment arm is no longer satisfied. Therefore, IY cannot be directly calculated using this formula. When this situation occurs, we need to use the parallel axis theorem. And since parallel axis theorem is now being utilized on this differential element, because these moment arms are actually varying along this differential element, so the parallel axis theorem will be considered on differential basis. So if you notice, the parallel axis theorem was given by Iy equals to Iy dash a bar plus area of cross section into the distance between the two parallel axes squared. So this d square here is the distance between the two parallel axes. So since I am trying to calculate Iy, I will see that which axis is parallel to y-axis. Obviously this x bar is not parallel to y-axis, but this y bar is parallel to y-axis. So I have to find out the distance, the perpendicular distance between these two axes, y and y dash. And you see that distance was actually the centroid of this strip, which was equal to x tilde or x by 2, right? So this distance between the two parallel axes y and y dash is equal to the centroid of this differential element, x coordinate of the centroid of this differential element, which is x tilde, which is equal to length of the differential element divided by 2, so x upon 2. And dA, okay, this dA is analogous to this A. So here it is written on the bulk level, here it is written on the differential level. So this dA would be equal to length of the strip x multiplied by thickness of the strip dy. So this diy is equal to diy dash or diy bar. They are the same thing. And this diy dash is actually the value of the second moment of area of this rectangular strip about the y dash axis, that is about its own centroid. Okay, and since it is a rectangle, we know that the value of second moment of area of a rectangle is given by 1 by 12 cube of the one dimension, while the second dimension being multiplied with the power 1. So the cube of the dimension will be the dimension that is perpendicular to the y-axis. So this dimension, that is the length of the strip, is perpendicular to the y-axis. So the length of the strip is x. So cube will be of x. This x, the length of the strip, will be cubed, while the dimension that is parallel to the y-axis, which is dy, will remain as it is. That is with the first power. So please remember that for a rectangle, the value of second moment of area was 1 by 12 a cube b, where a and b are the dimensions of the rectangle, but you have to decide that which dimension will be cubed and which dimension will not be cubed. So here, since we are calculating Iy, the dimension that will be cubed will be the dimension which is perpendicular to the y-axis, this dimension x, while the dimension that is parallel to the y-axis will remain as it is. So this is dy, the dimension that is parallel to the y-axis is dy. So using the parallel axis theorem now, we can write that the second moment of area of this entire cross section about the y-axis is equal to the value of the second moment of area about the centroidal axis of this differential element that we have considered, which is 1 by 12 x cubed dy, plus the distance between these two parallel axes, that is x by 2 square, multiplied by the differential area of the strip element, which is equal to x dy. So this will become x cube upon 4 dy, and this will become x cube dy, and you can take x cube dy common to write 1 by 12 plus 1 by 4, which is, yes. So I was telling you that you can actually take this common x cube into dy common, and here you will get 1 upon 12 plus 1 upon 4, which will going to reduce to 16 upon 48 x cube dy. Now since here we have to perform the integration with respect to y, so we have to eliminate this x. Okay, so from this given function y cube equals to x square, we can write that x square is equal to y cube, and so therefore x will become equal to y raised to the power 3 upon 2, and then substitute the value of x square and x here in place of x cube. So x cube can be written as x square into x. So using integration both the sides, that is, you have to apply integration here and you have to apply integration here. In place of x cube, you can write x square into x, that is equal to y cube and y raised to power 3 upon 2. This 16 by 48 will come out of the integration sign, and this will be further reduced. These y will further be reduced to y raised to power 9 upon 2. And now it is fairly simple to integrate this. Okay, so it will then become y raised to power 11 upon 2 divided by 11 upon 2. Okay, so you will going to take the limit on the y-axis, because you are integrating with respect to y-axis, so you will going to take the integration on the y-axis. The limit on the y-axis is 0 to 1 meters. Okay, you substitute all the values here and you will going to get the same result, that is Iy equals to 0.061 meter 4. So this answer is the same answer that we have received when we considered the vertical strip on the previous slide. So you realize the difference now. The work that we have performed was rather simple when we have considered the vertical strip, and this was because we can directly use the formula for Iy, which was equal to integral x squared dA, because of the fact that when we are using the vertical strip, the moment arms measured from the y-axis and along the x-axis, they remain same on the strip length, while if we consider the horizontal strip, uh, the condition for equal moment arms is not satisfied, and therefore we cannot directly use this formula. Rather, we have to use the parallel axis theorem on differential basis. Okay, but the end result will be the same, the answer will be the same. So it depends upon the choice of your strip. If you have uh, intelligently selected the strip, you might reduce your work and make it more simple. But if you have selected a horizontal strip, then your work can become tricky, because you have to use then the parallel axis theorem, and you have to be more careful in your calculations. So anyway, you have to go through both these procedures and notice the difference. And because you could be asked in the final exam uh, to use only the horizontal strip or only the vertical strip. So the choice will not be arbitrary, as it was in the last chapter, chapter number 9. So you have to go through both these methods thoroughly. So we're going to meet in the next lecture, and we'll continue solving